Hello everyone, this is Pavan. I'm back again with another video. So today I'll be solving the problem 1319, number of operations to make the network connected. Okay, this is a problem related to graphs. This seems looking like a complicated stuff, but it's actually an easy problem. I too felt it's something like a complex problem, but later I realized that it's not that hard. So there are n computers from 0 to n minus 1 connected by Ethernet cable connections, forming a network where connections of I is A comma B. That means there will be an edge between the A and B, represents a connection between the computers A and B. Yeah, any computer can reach any other computer directly or indirectly through the network. Okay, given initial computer connections, you can extract a certain cables between the two directly connected components and place them between any pair of disconnected components. Okay, to make them directly connected, return the minimum number of times you need to do this in order to make all the computers connected. Okay, if it is not possible, we should return -1. Let's see the examples. So if these are the four computers, we can remove this edge and connect this to it, and another choice can be remove this and connect 2 to 3. This will also connect the whole network, right? For this example, so here the answer is going to be 1, because we are removing this edge and connecting these two or these two. Here in this case he has connected these to 1 and 3. In this case, we can remove these two edges which are kind of X symbol, and we can connect the one with these two and another with these two, right? Anyway as well, anyway we he has considered the another case. We, instead of connecting this one, we can connect these two as well. The whole idea is, after connecting, we should be able to traverse from any node to any node, right? That is actually called as connected, right? If the graph is connected, that means we can travel from any node to any destination, right? But here they have given some disconnected kind of components, and we need to connect them, and so that we need to calculate how many operations we'll do. Operations in the sense, we are removing these two in this example, right? And connecting the making the connections between two computers so that all of them are connected, right? So we are making two operations by removing them and connecting them. We need to calculate those operations. Okay, that is the that's the problem actually. What we need to do is, the approach I have followed is, if there are n nodes, how many edges will be there actually to connect all of them? See, if there are 4 nodes, 3 edges are enough, right? See, 3 edges are enough actually. If there are 6 nodes, 5 edges are enough, right? See, 1 2 3 4 5. If you consider any graph, if there are n nodes, that means n minus 1 edges are required to connect the graph, right? So that's it, that's the actual logic, right? We need to find connected components in the graph, and then we need to unnecessary nodes in this graph, then we'll connect with them, right? Okay, so if I code it, then that means that will be pretty much clear to you. So let's create the graph with the given connections. So vector int edge list of n plus 1, not n plus 1, it's n only, because it's given that 0 to n minus 1, right? So we'll traverse from 0 to n. Is it n, or I guess it should be connections dot size of, I guess, int edges is equal to connections dot size of. I'll traverse through the vector and construct the graph. Okay, edge of int a is equal to connections of I of 0, int b is equal to connections of p of 0. Okay, so for a will push b, then for b will push a. Okay, as it is undirected, right? So we need to connect both of them. Okay, so our graph is connected. Now what we need to do is we need to perform the DFS traversal. For the constructed graph. Okay, so these can be the parameters, and one thing is our node, the source node, and one more thing we need to keep track of is visited array as well, right? Visited not array, it's matrix. Okay, and what I am approaching, what's my approach is I'll find out how many connected networks are there. In case of here, the connected networks are, this is one connected network, this red one is one connected network, two networks are there. Here as well we have three networks. This is one network, this one is network, this one is another network, right? I'll visit the current node, then I'll traverse through the neighbors of the edge given graph, given source node, right? If the child is not visited, we'll perform the DFS. Okay, we need to pass the adjacency list, and the source node is going to be child node and visited matrix as well. That's pretty much with the DFS. As there are disconnected components, we need to traverse through the graph. I is equal to 0, I less than n, I plus plus, and if I is not visited, we'll make the DFS call, and we'll increase the connected components. Let's call it as CC. Okay, I need to declare the CC here. And one more thing is we haven't declared the visitor matrix, right? Visited, I think it should be single dimensional only, right? Yeah, that's it. So we have calculated all the connected components, right? if I try to print the CC, let's return some dummy value. If I try to print the connected components, I'll be getting number of connected components, right? It's taking too much time actually. There is something wrong here. For okay, the DFS, okay, we need to place auto or int, whatever it may be. That's okay. So I think you got it. We need to find the connected components. That's an important task to do here. Here the STD standard output is 2. In case of this one is 0 1 0 2 1 2. This is the example. So here we have two connected components, right? That's why it have given the standard output as 2, right? So we have find the connected components. That's the important task to do for this problem. So major task is completed. Now the important important task is we have find the connected components, and how many edges do we have? Actually we have 3 edges here, right? Edges are nothing but the connections dot size of, okay, these are the edges, right? We have edges as well, right? So we have the edges and we have the connected components. Can we do anything with that? Here we have two connected components and 3 edges, right? We can connect them by so connected components are 2, and what we need to return the minimum number of times you need to do this in order to make all the computers connected. Okay, we have find the connected networks. So the thing we need to do here is for this one the connected components are 2 and edges are 3. For this one the connected components are 3, the edges are 5. 5 minus 2 is 3. That's not a good option. 3 minus 2 is 1. When it is not possible, actually, if it is not possible means if edges are if there are n nodes, there should be n minus edges, right? So edges plus 1 should be equal to nodes in the sense n is the nodes given to us, right? It should be they should be equal. If there are they can be edges can be greater than as well, but it should not be less than n, right? That can be the invalid graph. That means invalid in the sense we cannot connect them, right? In such case we need to return the -1, right? Here they have mentioned to return -1 if it is not possible. Edges plus 1, okay, then we can definitely make the connections, right? So we need to connect all the connected components. If there are 2 connected components, that means we need to make one edge only here, one operation only. If there are 3 connected components, that means we need to make only 2, that means CC minus 1, right? So I think that should be fine, I guess. Let's see. Okay, it's not required. This one is let's working. Let's see if it is working for the, yeah, it's got accepted. I think, see, in this problem, if you find the connected components, that's pretty much it. You see, if for this example the connected components are 3, right? So the connected components are 3 means three components are not connected, right? We need to connect all those three. For all those three, how many connections are required? We need to perform two operations, right? Because we need one wire between the first component and second component, and another wire between second component and third component, right? So the cc minus 1 is going to be the answer, right? When we can't do it means if there are edges which are not enough to make the network connected. In case of 3, if there is one edge means we cannot connect both 3 of them, right? So that's pretty much. The DFS traversal is prerequisite for this problem actually. Other than that, the problem is very much simple actually. I hope you understand the problem and understand the logic as well. Thank you for watching. I am back again with another video tomorrow. Thank you so much.